Björn Wehlin, PhD student in the topological data analysis group in the math department at KTH in Stockholm. I'll give you a brief introduction to my Python package masspcf that is used for working with piecewise constant functions. So why do we care about piecewise constant functions? Well, you have your Betti curves, or your characteristic curves, stable rank, which we'll do a little bit later in this tutorial. So for common data analysis tasks in TDA, you want to be able to work efficiently with piecewise constant functions. I will generally assume that you already know what TDA is, at least a little bit. What is a persistence diagram of typical inputs and so on. But just to set the stage here, we have a data set where each instance is represented by a finite point cloud. From this, we can compute a persistence diagram or a set of persistence diagrams, in this case for the 0th and 1st homologies. And now we want to do some statistical analysis. And typically to do that, we want to have some sort of vector representation of this persistence diagram. And what I will work with right now is functions like this. So you have, you can think of this as time, and then you have your filtration going in time here, and then you have some values of your function. And because you have only finitely many points, this function will only change it finitely many times. Now for actual data, the idea is that if you have instances that look similar, you should get similar looking representations. And if you have different data, then you should get different looking representation. And by different here, I mean maybe in the L1 distance sense. For example, you take the integral distance between the functions. You run this across your whole data set. You get a distance matrix like this. And this you can then use for downstream analysis, for example, clustering, k-nearest neighbors. If you do a kernel matrix instead, you could do SVMs. We'll do a little bit of clustering here in a moment. One thing we have to be aware of when we work with piecewise constant functions is that they are not as nice in some sense as just arrays of numbers as you would have in most applications. You can have lots of change happening quickly in some of them, and some of them will change more less often. If you work with them now, you have to come up with ways of computing with them, and all of this writing of infrastructure and so on that will detract from you're making progress towards your actual data analysis that you're interested in. This changing times also makes it difficult in terms of storing these things. But all of this has been solved in masspcf for you. And this is a high-level overview of the library. And at the bottom here, we have n-dimensional arrays of piecewise constant functions. This is similar to libraries like NumPy or PyTorch and so on, where you have n-dimensional arrays or tensors of numbers. Here, instead of numbers, we have piecewise constant functions. You can plot them, but more importantly, we have the algorithms. And that is distances, kernels, reductions, taking the mean, for example. So if you do some subsampling, let's say you take 10 subsamples per instance, and you compute the topology for each such subsample. And then maybe now you want to average all of those topological descriptors. You can use mean reduction to do that. To actually run the algorithms, masspcf behind the scenes for you. You don't have to worry about this. It does it automatically. It will send off the computation to either several CPU cores, or if you have a CUDA-capable GPU or several CUDA-capable GPUs, it will partition it out to those as well. So that makes it possible to run quite large things. Also, it will be fast for smaller instances. Now let's get to actually writing some code here. And this notebook will be available. Also, I will not go through installing the prerequisites and so on. This will be NumPy and Matplotlib and so on. The important part, of course, here is installing masspcf. If you want the details, just go to the documentation page. But what you need to do is you say pip install masspcf-cpu if you want the CPU-only version. The backend of masspcf is in C++ and CUDA, so there's some compilation necessary. If you do masspcf CPU, it's already pre-compiled for you, so that will just simply download the binaries. If you want the full capability of the library, you do need to use this masspcf package instead. You do pip install masspcf. But then you do need to have a CUDA toolkit installed and a C++ 17 or above compiler installed. So what are we actually going to cluster? Well, let's pick a data set that is familiar to most people. We'll go with the MNIST data set of handwritten digits. And if you haven't seen it before, it looks something like this. I've stripped out just the 1s and 8s here. So what they are, they're 28 by 28 grayscale images of handwritten digits. And the reason for 1s and 8s is that topologically 8s sort of have 2 holes in them and 1s don't. But the ones maybe aren't looking the same for all of them, for example. We'll skip through how to actually produce the point clouds and get to the result of that process. And we have the original data on the left. We have the point cloud that's produced on the right. So that's essentially just sampled from these points in the image. But I've also added a little bit of noise here to make the persistence diagrams a bit more interesting. You'll see for an 8 like this, we have 2 significant H1 features, as you would expect. If we look at a 1, that's not really the case anymore. So now let's get to vectorizing the persistence diagram. We can use stable rank. It's one vectorization. I will say that this is a simplified case of stable rank that we're using. It is more general in its construction, but if you want to read more, either pause the video and read this right here, or you can look at this paper. This is the closest one to what we're doing. And then if you want to read more, you can go into these maybe. But suffice to say, so what you have, okay, we have a function that takes a persistence diagram. It's called compute stable rank. It does some basic things with the diagrams, not terribly complicated, and then returns a NumPy array corresponding to the stable rank of that, corresponding to that persistence diagram. I will use Ripser to get my persistence diagrams. You can of course use Goody or whatever other library you're familiar with, and then you say, okay, let's take Ripser and get the persistence diagrams for H0 and H1. xCloud here is my point cloud data. So we have on the first dimension here, we have the different digits, handwritten digits, and then we have X and we have Y points. I compute the stable rank, we get something like this. It's just a NumPy array, n by 2. We have the change points of the function on the x-axis. And then on the y-axis, we have the values of that function. So then we're finally getting to masspcf. We're now going to bring this array of numbers into a piecewise constant function that we can operate on. That we do by first importing masspcf, of course. I will do it as mpcf. And then you use this PCF class here. So you say mpcf.pcf, you pass it this array of numbers, and now you have a piecewise constant function, which we can then go ahead and plot. So the way you plot that is you will then use the plotting module. There is this plot function in masspcf.plotting. I've called it PCF plot. I'm going to go ahead and create 2 subplots here with pyplot. One will contain the persistence diagram, one will contain the stable rank. So I have 2 axes. I use the persim package to plot the diagrams. So I give it the first or 0th axis. And then I use PCF plot to plot this stable rank that we've computed here as a PCF. That's right here, and the axis is the axis number 1. And the remaining arguments get passed on to pyplot. Let's run that. And it looks something like this. So here's the persistence diagram. I chose to plot the lifetime representation as opposed to this diagonal one. And then we have the piecewise constant function, the stable rank, corresponding to H1 here. Now, to do actual analysis, we need to work with arrays of PCFs. So we can create an array of 0 PCFs. So 0 PCF is just a PCF that has the value 0 at 0 and keeps going at 0. So I'm going to create a 10 by 3 by 5 such array. And if we print out the shape, it will display its shape 1035, as we would expect. Now let's start this off and let this run in the background. To do the clustering will run in quadratic time, so it will restrict the number of points a little bit here. So we'll just do the first 5,000 instances. That should be plenty to look at something anyway. I then create now a zeros array again, but I will have 5,000 by 2. And the reason is that on the 0th column I will have H0, and on the first or second column I will have H1. I go through my data set, I compute the persistence diagrams, I use the compute stable rank to get the 0th homology and first homology stable rank as NumPy arrays. And then I put them into my matrix of PCFs. So in the IDX row, 0th column, I put a PCF corresponding to the H0. And in the IDX row, first column, I will put the H1 PCF. Then PCF plot will let you plot not only a single PCF, but also multiple PCFs if you have a vector of PCFs. So by a vector here, I mean an array with only one dimension. And here I'm picking out 10, 11, 12, and 13th PCFs. I'll do the first column. So this is the same syntax as you would have in, say, NumPy. And we can plot that, and it looks something like this. Of course, we can also do the 0th column, and that will give us the H0s. Now, to do the clustering, okay, instead of just clustering on H1 or something like that, then let's have a little bit of fun. So we'll build a derived feature. So what I'm going to do is I'm going to take the average between the H0 and H1 for each instance, and we'll cluster on that. And the way to do that is to say mpcf.mean, you give it your PCF array, and then you say which dimension to reduce along. So this will reduce along the first dimension, meaning that for each row we'll compact the two columns into one column. And run that runs essentially immediately. And I can print out the shape, and it's a vector of 5,000. Let's plot that just to see what it looks like. We have for H0, we have the blue one. H1 is the orange one, and the green one is the average. And you can see it's the pointwise average between the two functions. So now we have 5,000 of these averages, and we're going to cluster based on that. To do the clustering, we have to compute a distance matrix. We can use the pdist function, pairwise distances. We give it our vector of distances, vector of PCFs, averages. We run that. That takes about a second to run on my system. And then we can look at the top 500 by 500 part of that distance matrix. Let's say it looks something like this. There's not too much structure here, just because the 5s and because the 8s and 1s occur overlapping in some sense. Let's do a t-SNE embedding on this. So this is the clustering. This will take high-dimensional data, bring it down to low-dimensional space, here 3 dimensions. I have to say metric pre-computed because I already have a distance matrix. I pass in the distance matrix, so it's this distance matrix, the full distance matrix. And now I can plot this embedding, and we get this fun plot like this where we can see that eights which are in blue, they get close together, and the ones that are red, they get close together.